So good evening all. So today we have element hydrides of group 15 जिसमें हमने उसका melting point, boiling point, bond angle, preparation that we have covered in our previous lecture. So today we will start with thermal stability. So thermal stability of element hydrides. Thermal stability की बात अगर करें हम तो as we go down the group तो क्या होगा, size of the element increases. Okay, तो element का size increase करता है as we go down the group. अगर element का size बढ़ेगा तो जो element hydrogen bond है, element hydrogen bond length increases. तो एलिमेंट हाइड्रोजन बॉन्ड लेंथ अगर इंक्रीज करेगी तो जो एलिमेंट हाइड्रोजन बॉन्ड स्ट्रेंथ है, इज इट विजिबल, एलिमेंट हाइड्रोजन बॉन्ड स्ट्रेंथ वो क्या करेगी बेटा, एलिमेंट हाइड्रोजन की जो बॉन्ड स्ट्रेंथ है दैट ऑब्वियसली डिक्रीजेस. ये वाला पोर्शन दिख नहीं रहा है. तो एलिमेंट हाइड्रोजन की जो बॉन्ड स्ट्रेंथ है वो डिक्रीज करेगी. दैट मींस ब्रेकिंग ऑफ एलिमेंट हाइड्रोजन बॉन्ड बिकम्स easier. So as we go down the group, nitrogen, then phosphorus, arsenic, antimony, bismuth, तो साइज क्या हो रहा है, इंक्रीज. So element hydrogen bond की length increase, bond strength decrease, and so thermal stability decreases. Thermal stability decreases. Thermal stability बेटा क्या हो जाएगी, decrease as we go down the group. That means सबसे स्टेबल कौन सा होगा, NH3, then PH3, ESH3, SBH3, and then BiH3. That means BiH3 is thermally unstable, means highly unstable element hydride of group 15 is bismuth hydride, right? I think it's clear to you. Have you any doubt? Okay, Manjot, Anika, where is Abhay? Okay, now second part. On the same line, if we compare reducing character, so reducing character in this case, when element hydrogen bond becomes weak, that means its breaking is easier, so its tendency to give hydrogen is more, and hydrogen is a reducing agent. That's why its reducing character increases. Or in other words, we can say if thermal stability of hydrides decreases, its reducing character increases, right? Means as we go down the group, then what would happen? As we go down the group, again same case, element hydrogen bond, directly I come to strength, element hydrogen bond strength decreases, so its tendency means what is it means hydride, element hydride, its tendency to give hydrogen increases, which acts as a reducing agent. Obviously hydrogen is a reducing agent. and that's why reducing character increases down the group. Reducing character increases down the group, or you can say that thermal stability and reducing character are inversely proportional. Reducing character is inversely proportional to thermal stability. Reducing character is inversely proportional to thermal stability. Okay, that means thermal stability decreases down the group and reducing character increases down the group. I think it's clear to you. Any doubt up to this? Okay. Now next part. Next part is basic character of hydrides. Basic character. Basic character of group 15 element hydrides. Basic character of group 15 element hydrides. So in this case, keep in mind, they are basic due to the presence of lone pair. Means they have ability to donate lone pair, and base is one which can donate pair of electron or which can give electron. Simple. Okay. So if you talk about ammonia, in ammonia it has 3 bond pairs and 1 lone pair. It is like this, right? It has 1 lone pair and 3 bond pairs. So ammonia has ability to donate electron pair. That's why it's basic in nature. Ammonia is basic in nature. Now as we go down the group, what would happen? If we talk in terms of electronegativity, electronegativity decreases. So actually electronegativity is related to attraction of the electron. Which electrons? Shared pair of electrons. Okay. Now there is the point of donation of a lone pair of electron. Okay. So as we go down the group, size of the atom increases, because whenever we go down the group, size is a dominating factor. Keep in mind, size of element increases and your lone pair remains one only. Lone pair is one, but size is increasing. So electron density, what do you mean by electron density? Electrons per unit volume. So electron density, because size increases, so electron density decreases. So as electron density decreases, ability of element hydride to donate electron pair decreases. Due to the decrease in the electron density, its ability to donate electron pair decreases, because now same number of electrons is on the larger size, larger volume. Okay, that's why as electron density decreases, its ability to donate it, that also decreases. So basic character decreases. That's it. That means NH3 is most basic, then PH3, ASH3, SBH3 and BiH3. Okay, NH3, PH3, ASH3, SBH3 and BiH3, because you know size increases, so electron density on the donor atom, on the central atom decreases, and so its electron donating power decreases, and so is the basic character. Okay, alternatively it can be explained by forming bond. It depends upon the element hydrogen bond strength. So as we go down the group, element hydrogen bond strength decreases, so its ability to accept H plus decreases. So in that way we can explain it, but it is the better way. Just write that as we go down the group, size of the atom increases, so its electron density decreases, and that's why ability of that hydride to donate electron pair, that decreases, and so is the basic character. Right? Any doubt up to this? Okay, next part. Now we have reactivity towards oxygen, or we can say formation of oxide. Nitrogen is smallest in size, and nitrogen ability to form strong p-pi bond. That's why maximum oxides are formed by nitrogen. Okay, so nitrogen can form N2O, it can form NO, or it can form N2O3, it can form N2O4, or we can say NO2, because N2O4 is dimer of NO2, that we have done already, because NO2 has an odd electron, and to acquire stability, to gain more stability, it forms dimer when it is cooled. Okay, then it is N2O5. So tell me, what is the oxidation number of nitrogen in N2O? Oxidation number of nitrogen. So in N2O, oxidation number of nitrogen is +1. In NO, it is +2. In N2O3, it is +3. In N2O4 and NO2, it is +4. In N2O5, it is +5. Okay, great. If you have no doubt, then it's great. Now, say in +1 state, only nitrogen can form oxide. Phosphorus, arsenic, antimony, bismuth will not form any hydride in +1 state. Now these are the elements. So N2O is not just like N2O. There is no P2O or AS2O or SB2O, Bi2O. NO, even NO in +2 state, only nitrogen can form oxide. It is because of the ability of nitrogen to form strong p-pi bond. Keep in mind, N2O3, just like N2O3, phosphorus can form P4O6. P2O3, it always form dimer. Reason being, because pi bonds are not strong in case of phosphorus. So it form dimer like P4O6. Same arsenic also form As4O6. Antimony Sb4O6. Bismuth even can form Bi, but bismuth can form Bi2O3. It is because of the metallic character of bismuth. It is not because of the ability of bismuth to form multiple bond, but it is the ability of bismuth to form bond with oxygen. Oxygen being non-metal, bismuth is metal. So in bismuth +3 and O2 negative. So it is crisscross Bi2O3. Okay, but rest of them form dimer. Now come to +4 state. So only phosphorus can form P4O8. N2O5, so it can, phosphorus can form P4O10. Arsenic can form As4O10, or it can form Sb4O10. That's it. So these are the oxides, first thing. Now come to compare the acidic character of oxides of nitrogen only. You know, nitrogen is non-metal. So nitrogen oxides, generally they should be acidic. So keep in mind, sorry, as is it visible? Yes. So as nitrogen is non-metal, you know, nitrogen can form either neutral oxides or acidic oxides. So oxides of nitrogen are either neutral or acidic. Okay, so as you know, oxidation number increases, acidic character increases. As oxidation number increases, acidic character increases. Why is it so? Because when oxidation number increases, its ability to get electrons, to gain electrons, to accept electrons increases, and that's why its acidic character increases. Okay, so that means what is the order of acidic strength? So N2O5 is most acidic, then it is N2O4 or NO2, then it is N2O3, and then NO and N2O. But NO and N2O are neutral oxides. They are neutral oxides, and their acidic character means N2O5, N2O4 and N2O3, their acidic character is like that, because as oxidation number increases, acidic character increases. Okay, so this is about nitrogen. Now come to compare nitrogen, phosphorus, arsenic, antimony, bismuth. So as we go down the group, you know what would happen? Non-metallic character, yes, non-metallic character decreases. And you know, non-metal oxides are acidic and metal oxides are generally basic or amphoteric sometimes. So in this case, as we go down the group, you know, non-metallic character decreases, and that's why their acidic character decreases. So if we compare these oxides, you know, N2O3 is most acidic, then P4O6 means order of acidic strength. Then As4O6, then it is Sb4O6, and Bi2O3 is not acidic because it is metallic oxide. Bi2O3 is metallic oxide. So you can compare up to this. Or generally, you know, non-metal oxides are acidic. Metalloid oxides are generally amphoteric. And metal oxides are basic. In general, I would like to say it is in general. It is not in actual. Okay, in actual we say non-metal oxides, nitrogen oxides, they are neutral. N2O, NO, right? H2O, amphoteric, you know. Done. So this is about metal oxides. Hydration energy. Wait, I let you know hydration energy. Actually, hydration energy same here, same metallic acidic character. It is like this. Okay, actually hydration energy is the amount of energy released when 1 mole of ions interact with water. Okay, like this is the question asked by Anandavali. Okay, like we have Na plus. So Na plus, when it is coming in contact with water, you know, like this, by ion dipole attraction. So energy released for 1 mole of ions by this interaction, that is called hydration energy. There is ion dipole interaction between water and ion. Okay, right. So next topic is reactivity towards halogens. Reactivity towards halogens. So you know, with halogens, element generally form two types of halides, EX3 and EX5. In general, again, EX5 and EX3, because it can form 3 bonds, or if electron is excited, because in element group 15 element, you know, we have NS2, NP3, NS2, NP3. So it forms 3 bonds easily and form trihalides. So if we compare it, it's means see its shape, again it undergoes sp3 hybridization. There is one lone pair and 3 bond pairs. So, sorry, 3 bond pairs and 1 lone pair. So it is trigonal pyramidal in shape. Shape is trigonal pyramidal. Or sometime what happened, one of the electron from, this is ground state. In this case, it is hybridized in the ground state. But if one of the electron is excited to vacant d orbital, means to form 5 bonds, element should have vacant d orbital. Keep in mind, element should have vacant d orbital so that one electron can be excited, and therefore it undergoes sp3d hybridization and it forms 5 bonds. So when 5 bonds are formed, they are arranged in trigonal bipyramidal geometry. There is trigonal bipyramidal shape. Trigonal bipyramidal shape in which these axial bonds are longer than equatorial bonds, because on axial bonds bond pair repulsion is more than that of on equatorial bonds. Means axial bonds are more repelled than equatorial bonds, and that's why axial bonds are longer than that of equatorial bonds. Done. So this is about the shapes. Now come to next part, that nitrogen. Yes, tell me. Is it possible for nitrogen to form 5 bonds? Yes, beta. Is it possible for nitrogen to form 5 bonds? What I said, is it possible for nitrogen to form 5 bonds? Fast. So it is not possible. The reason being, nitrogen does not have vacant d orbital. Nitrogen does not have vacant d orbital. Therefore, it cannot extend or cannot expand its covalency beyond 4, because it has only 4 valence orbitals. Due to the absence of vacant d orbital, nitrogen does not form pentahalide. So nitrogen does not form pentahalide, means NCl5 does not exist, but NF3, NCl3, NBr3, Ni3 do exist. Okay, out of them NF3 is an exothermic compound, because nitrogen and fluorine both are small in size, So they can form strong bonds. That's why NF3 is an exothermic compound. It is stable. Rest of them, they are not so stable. Okay, NCl3, NBr3, Ni3, their bonds are not very strong. Okay, so if we compare their stability, NF3 is most stable. Okay, now rest of them can form 5 bonds. Rest of them can form 5 bonds. So if we compare nitrogen, phosphorus, arsenic, okay, sorry, is it visible? Yes, nitrogen, phosphorus, arsenic, antimony, and bismuth. So nitrogen can form fluorides. Fluorides, trifluoride is formed by all the elements. PF3, ASF3, SbF3, or BiF3. Okay, so trifluoride is formed by all. Okay, now chlorides, NCl3, PCl3, Vandana Gupta, hello beta, ASCl3, SbCl3, BiCl3. So trifluorides, trichlorides, they are formed by all the elements. Okay, now come to bromides. So NBr3 is highly unstable, therefore it is formed in the form of its ammoniate. NBr3 is unstable, therefore NCl3 even it is also unstable, but NBr3, that is in the form of ammoniate only. Okay, NBr3, then PBr3, ASBr3, SbBr3, BiBr3. Then come to iodides. Nitrogen can form iodide, but it is highly unstable, therefore it is in the form of ammoniate. Nitrogen triiodide in the form of its ammoniate is stable, otherwise it is unstable. Pi3, ASI3, SbI3, and BiI3. So if we compare their stability, so as we go down the group, stability decreases. Stability of halides decreases. Okay. Now fluorides, then pentahalides. Okay. So nitrogen, phosphorus, arsenic, antimony, and bismuth. So if we compare their pentahalides, nitrogen cannot form fluoride, chloride, bromide, iodide. In penta state, it cannot form pentahalide, nitrogen, because of the absence of vacant d orbital. Just now I have explained. Okay, why nitrogen does not form pentahalide. But PF5, AS, F5, SB, F5, BiF5. Keep in mind, bismuth can form pentahalide only with fluoride. Rest, chloride, bromide, and iodide does not exist for bismuth. Means bismuth can show +5 oxidation state with fluorine only. And due to inert pair effect, bismuth in +3 is more stable than bismuth in +5. That is also the reason. Okay. Now PF5, PCl5 does exist. PBr5 also exist. But PI5 does not exist. Even means iodide, penta-iodide for phosphorus, arsenic, antimony, bismuth do not exist. Okay, phosphorus can form PF5, PCl5, PBr5. Okay, arsenic can form pentachloride, bromide is not formed. Antimony can also form pentachloride, pentabromide does not exist. So see, if we compare nitrogen, there is no pentahalide. For phosphorus, PF5, PCl5, PBr5 does exist. Okay, arsenic and antimony, only pentafluoride and pentachlorides, pentachlorides, bismuth form only pentafluoride. That's it. Okay, now you know PCl5 in vapor state exists like PCl5 only. Okay, means it has trigonal bipyramidal shape. Where axial bonds are longer than equatorial bonds, and when PCl5 is heated, it forms PCl3 and Cl2. That's why PCl5 is a chlorinating agent. PCl5 is a chlorinating agent. Okay, but if you say PCl5 in crystalline state, or we can say solid state, PCl5 in solid state exists as ionic solid. Very, very important. What is the hybridization of phosphorus in solid state? Hybridization of phosphorus in PCl5 when it is in crystalline state. If PCl5 in the vapor state, okay, then its hybridization is sp3d2. Sorry, sp3d. PCl5 in vapor state has hybridization sp3d. And what is the hybridization of phosphorus in solid PCl5? First I write PCl5 in solid state exists as an ionic solid, and that is like PCl4 positive and PCl6 negative. PCl4 positive and PCl6 negative. Okay, so if question is what is the hybridization of phosphorus in solid PCl5, so say it exists as PCl4 positive and PCl6 negative. So you know in PCl4 positive, well, solid PCl5 exists like this. So PCl4 positive, you know, in PCl4 positive, hybridization of phosphorus is sp3, because phosphorus has 5 valence electrons. Out of 5, 1 is removed as positive ion, so it has 4 valence electrons, and 4 are utilized by chlorine, by 4 chlorines. So there are 4 bond pairs and no lone pair. Therefore here it has tetrahedral shape. So in PCl4 positive, it is tetrahedral, and come to PCl6. So in PCl6, there are 6 bond pairs and no lone pair, because phosphorus has 5 valence electrons, 1 is gained as a negative ion. So there are 6 electrons Out of 6, all the 6 are utilized. So it is like this. So its shape is octahedral, and hybridization of phosphorus is sp3d2. sp3d2. So hybridization of phosphorus in PCl6 positive, PCl6 negative, it is sp3d2. So if question is what is the hybridization of phosphorus in solid PCl5, you will write it is sp3 and sp3d2. Don't write sp3d, that is in PCl5 in vapor state. If question is simply what is the hybridization of phosphorus in PCl5, you will write sp3d. But if question is what is the hybridization of phosphorus in solid PCl5, say special mention of solid PCl5, then you will write it is sp3 and sp3d2, because in solid PCl5 is an ionic solid which exists as PCl4 positive and PCl6 negative. Okay. Simardev, yes, I remember you. Okay. Next is hydrolysis of these trihalides. Hydrolysis of trichlorides of group 15 elements. Hydrolysis of ECl3 of group 15 elements. So see, we have NCl3, PCl3, ASCl3, SbCl3 and BiCl3. Now hydrolyze. So what are the products formed? Can you write? Okay, Manjot, Anika, hope you are there. Just write their products. So yes, beta, tell me. So say NCl3 when it is hydrolyzed, it will give NH3 along with HCl. Sorry, along with, you know, H, nitrogen is negative, so to gain H plus, so NH3 along with HOCl, hypochlorite, HOCl. That means it is 3HOCl and NH3. Now PCl3 when it is hydrolyzed, it will give H3PO3. Reason being, now phosphorus is plus 3. Say in first case nitrogen is minus 3. Oxidation state of nitrogen is minus 3. So it will get H plus ions. But in PCl3 and others, it is plus 3. So it will gain OH negative along with HCl. Okay, same is the case with SpCl3. Sorry, AsCl3. It will give H3 AsO3 and 3 HCl. But SbCl3 and BiCl3, they are hydrolyzed in different way. Here SbCl3, when it is hydrolyzed, it will give oxychloride, SbOCl or BiOCl, Bi SbO and Cl negative, BiO and Cl negative along with HCl. So say the difference. In first case, NCl3, that will give NH3 and HOCl, PCl3 and AsCl3, that will give phosphorus acid and arsenic acid along with HCl, 3HCl. But SbCl3 and BiCl3, that will give SbOCl and BiOCl. Okay, antimony oxychloride and bismuth oxychloride. Okay, so that implies ease of hydrolysis. What is the ease of hydrolysis? Most easily hydrolyzed. I am from IIT Kharagpur. Simardeep Singh. But I think I don't know. Could you tell me? Nice to see you on my platform. So you can help other students. So ease of hydrolysis. So NCl3 is hydrolyzed most easily, then PCl3, AsCl3, SbCl3, okay, and then BiCl3. Okay. Now come to bond angle. See, if we have NF3, yes, Simardev, PF3, PCl3, PbR3 and PI3. If we compare their bond angles, you know, there is one lone pair and attached to halogen. So as electronegativity of halogen increases, as electronegativity of halogen not increases, decreases, okay, you know, it decreases along. Fluorine is more electronegative than chlorine, then bromine, then iodine. So as electronegativity of halogen decreases, bond pairs are closer to central atom, that is phosphorus. That's why bond pair repulsion increases, because bond pair goes closer as electronegativity of central halogen decreases, and therefore they come closer to each other. Bond pair repulsion increases, okay, and bond angle increases. That means bond angle is minimum in PF3 and maximum in PI3, right? So this is about element halides. So we have compared all these. Okay, tell me, Anika, Abhay, have you any doubt? Or any other who is watching? Yes, beta. Any doubt up to this? And if we compare trihalides of nitrogen जो है, they are least stable. Other, okay. Yes, Anika, Manoj, Abhay, Manjot, sorry. Even if question is like that triammoniates of iodide, nitrogen triiodide, if it is heated, we get N2 along with I2 and ammonium iodide. So if the question is like this, it is 8 moles, 5 and 9 and 6. Okay, so that's all for the day. Thank you so much for watching this video. God bless you all, and do subscribe my channel and share with your friends.